Alright, this video is going to be on the intermediate value theorem. Which we refer to as IVT for short. And the intermediate value theorem talks about the continuity of functions, and so it's appropriately placed in the unit. And first we're going to go ahead and write down what the definition of the intermediate value theorem is, and then we're going to go ahead and work with it. So the definition says that if f, so if a function is continuous on the interval from a to b, including a and b, and n is any number between f of a and f of b. So here we're saying that n is a y-coordinate. So n is the y-coordinate that is between the y-coordinate you get when you plug a in and the y-coordinate you get when you plug b in. So n is any number between f of a and f of b where f of a doesn't equal f of b. So we're not talking about a perfectly horizontal line here. It means they have to be evaluated at different numbers. Then there exists a number c in AB. So now we're saying it's inside of AB, so it can be between the numbers a and b, but it cannot include those. So c and a can't be the same number. C and B can't be the same number, it has to be between them, such that f of a equals n, or not f of a, f of c equals n. So we're going to draw a little sketch of this because that's really weird. So here I'm saying if I plug in a, then I get f of a. There's my x-coordinate and my y-coordinate. And then we're saying if I plug in b, I get f of b. And then we're saying something happens where this could, it can go up and kind of, yeah, something like this. I don't know, some weird curve. All right. Then we are saying that there is some c value. So some c value right here, so that f of c equals n. So f of c equals n. And we're saying that that n value is in between f of a and f of b. That's what continuity means. So basically what this is telling you is that in any continuous function, you have to hit all of the values. So if I know that I have an interval where it's continuous, I can always make the assumption that there's some x between these numbers that's going to hit some y in between those numbers. So for example, we're going to show that f of x, the function x to the third plus 2x minus 1, has a 0, and that's another name for x-intercept, has a 0 on the interval (0, 1). So those are the x values that were in between. So if we go back to this definition, the first thing we want to know is we want to make sure that it's continuous on the interval. It's got to be continuous on AB. And we're going to say that f of x is continuous on 0, 1. And the reason we know that for sure is because this is an example of a polynomial, and polynomials are continuous on their domain, which is from negative infinity to positive infinity. So the function is continuous on 0, 1 because it's a polynomial. And then after that, we want to go ahead and evaluate the function at f of a and at f of b. So second, we're going to say f of 0 and f of 1. We want to evaluate the function for both of those values. So if I plug 0 in, I get 0 to the third plus 2 times 0 minus 1 is just negative 1. And then if I plug 1 in, I get 1 to the third plus 2 times 1, so that's 1 plus 2, minus 1 is just 2. So evaluate the functions. And now we want to look to see if n is a number that could be in between these. And the answer to that is yes, because we are looking to make sure that the 0 of the function, and if you have a 0, that's an x-intercept, that means that the y-coordinate there is going to be 0. So we are trying to see if I can plug 0 into the function and have that be less than 0, and have 0 be less than if I plug 1 into the function, and that's true, because f of 0 is negative 1, and f of 1 is 2, and 0 is in between those numbers. So since that is the case, we can conclude that by the intermediate value theorem, there exists some c on 0, 1. So there's going to be some number in between 0 and 1, not including 0, not including 1, but some number in between, such that f of c equals 0. Okay, and we're going to go ahead and do one more example similar to this. We're going to show that f of x equals x to the third has a value of 5 on the interval 1, 2. So again, the first step is to make sure that the function is continuous on the interval 1, 2. And just like the previous function, we can conclude that it is continuous because it's a polynomial function. Because it's polynomial. I'm going to start to shorten it a little bit. The next thing that we want to do is we want to evaluate the function at 1 and evaluate the function at 2. And we want to make sure that 5 falls in between those numbers when we evaluate it there. So if I plug 1 in, f of 1 is just 1 to the third, which is 1. F of 2 is 2 to the third, which is 8. And it is correct to conclude that 5 is between 1 and 8. So that applies. And so based on that, we can say that by the intermediate value theorem, there exists a c on 1, 2, such that f of c equals 5. So there is some x value I can plug in to x to the third that would make 5 as an answer for the y-coordinate.